To get going with this, I would start from direct current, and the best representative that I could find to explain this to you would be a battery. So let's say a normal 1.5 volt battery. You all know those. You put them in your remotes. And something like that always has two poles, a plus and a minus. And you have to take care of them. You know that because you have to take care of those when you put them into your remote controller. This is the same kind of a battery you have in your phone, like the one I have in this Surface Pencil. And this battery is the best example I can find for direct current, and I'll show you why. So let's say next to this battery, we have something that consumes energy, let's say a light bulb. And if I connect this battery to the light bulb, like that, so plus and minus to it, the electricity in this example, and any other example involving direct current, always flows in the same direction, from minus to plus. The most important thing to get from here is that the electricity always goes the same direction through this cable and through this light bulb and this battery. So that is the main point around it. And we don't use this direct current only in remotes and flashlights and phones and such. We use this direct current in our computers too. So if I had to represent this direct current to you using a graph, and I know how much everybody must love graphs, but it's the easiest way to understand. So if I was to explain this to you through a graph, you would see that on this dual axis graph that has the amp and time, so we have two axes, amp, which can be positive, negative, and time. Direct current always stays on the same side of the graph. So it always flows in one direction. Yeah. And it can also vary. It doesn't have to be flat like this. This would be a battery. It would always stay at 1.5 volts, like one battery. If we connected two of those, we would get 3, and so forth. But it always stays on the same side of the graph. It's one way. It goes through the cable in one direction, always. And we use this direct current for, let's say, everything in our computers. So you know that computers, they have all those ones and zeros, the binary code they use. This is how computers work. So the only thing a computer knows inside is ones and zeros. And how this is represented by a computer is using direct current. And to be more specific, a 1 is a presence of electricity, and 0 is absence of electricity. So we have electricity, that's a 1. We don't have electricity, 0. Don't have electricity, 0. Don't have electricity, 0. Then let's say we again have electricity. And then again we have it. And again we have it. And these are all ones. So again a 0. Then let's say a 1. And this is how binary code exists. By alternating the presence of electricity and absence of it, we can encode ones and zeros. Now that we have this direct current covered, and covered in a sense, you know what it means. You know that through the cable, direct current always flows in the same direction, from a minus towards a plus, and that's it. Now that we have this direct current covered, and you know it always flows from a minus to a plus, so it always flows in the same direction through a cable, we can go over the alternating current. And what would that entice? So to explain this to you more easy, and so that you can actually see the difference between the direct current and the alternating one, I'm going to draw the simplest waveform of it, the simplest shape of alternating current. And that's a sine wave. Looks like this. You can see that now on this graph we have the positive side and the negative side of it, which means that on this part of the graph the electricity flows in one direction, and on this other one that is on the lower negative part of the amp axis flows the other way through the cable. So if we had, again, the same principle, if we had a light and we had, of course, two cables connected to it, of course, and then we have an alternating current power source, which is, let's say, any power outlet you have in your home. So in those we connect these two wires. The electricity would flow this way and come out the other way. But then the very next second, Well, this example I just draw is this part of the graph. But now what about this part of the graph on the minus side? Now on that part of the graph, the electricity flows the other way. Goes like that. Now this alternating behavior is why we call it the alternating current. So going one way through the cable and then the other way through the cable, it alternates. So let's say that this part of the graph that we just mentioned, the plus, makes it go that way. And then very next second, this part of the graph makes it go that way. And it changes its direction 60 times a second in the USA, in the outlet, and 50 times in Europe. So this change of up, down, and then back to zero again. So the moment it reaches from zero, goes upwards, back, and reaches zero again, that's one oscillation. That would mean 1 hertz, one oscillation per second. So if this direction change, going forward, then going backward, would happen once every second, it would mean that the current has 1 hertz of frequency. If that was to happen 2 times in a second, it would have 2 hertz of frequency, which means that in the USA, the electricity from the outlet has 60 hertz. 60 times every second, it goes back and forth. In Europe, 50 times. That's what it means. So the alternation of going plus, going minus happens once. That's one oscillation. How many oscillations we have in 1 second gives us the frequency. This is going to be very important, knowing frequency, because we are going to be using this term a lot. And it's very important what it actually means on a graph just like this, because this graph is really not too far away from representing sound waves that we will be seeing every day when dealing with music production. So there is one more thing left to explain concerning alternating current. As you can see it on this graph, the amp is here at 0. So at this point, and the next one, and the next one consequentially, because this could continue, all of those is where electricity doesn't flow at all. And I'll explain to you how. Well, it doesn't flow, then it starts flowing stronger and stronger and stronger and stronger in one direction, and this is where it's the strongest, flowing in that plus one direction. And then it slowly dissipates, attenuates, slowly, going downwards, then no electricity. Then it starts flowing the other way around, and this is where it's strongest, going the other way, in the other direction. Then it attenuates, the current becomes less powerful until it reaches 0, starts flowing the other direction, and so forth. Now when you consider this is all an analog signal. Analog signal because, as you can see, all of these values are continuous. So the current actually continuously flows through the cable. Now let's go over digitalization of those analog signals I just showed you. So what you have seen so far is this analog alternating current signal. It changes its direction many times a second, of course, but we will get to that. And now as we have it, we have 2 axes on this. So time and amp, and we have that signal of sine wave. We don't even need that much. So to explain to you how we are going to digitalize this is, of course, concerning resolution, because, you know, everything inside a computer has a resolution. Every digital signal has a resolution, just like every digital file. So let's say you have a digital image, and that image has some resolution, so times by something, you know, a number times a number, like an HD resolution of 1920 times 1080, and you have so many pixels to fit there, and that's it. One pixel has one color. It cannot have 2 colors in one pixel. This is how it also works for sound. So consider that if we have 2 axes like this, time and amp, this is how we get our sound resolution. So we have 2 resolutions, horizontal and vertical. Horizontal would be one of frequency, and vertical would be one of amplitude. But frequency, and I say that because it considers time. So let's explain that first. In order to digitalize this analog signal, which is continuous, as you can see, it's a continuous voltage change, stronger in one direction, falls off as we talked about it, and then stronger in the other direction, then falls off and back, and so forth. The way a computer would digitalize this signal to actually remember it would be to divide this timeline into regular intervals. And at each one of those regular intervals, it will remember the value that the voltage, that the signal had at that point in time. So a discrete value of the signal at that point in time, as such. Now, this is how a computer would remember this signal. I'm not going to draw any more of these. We had enough. So now that we have that, once this is gone, when a computer needs to recreate this signal, he would just connect the dots again. Connect through the dots. My bad drawing, but connect through the dots and get the same signal. If we had this digitalized all the way, it would just give us the same sine wave again. So once we have that, we have these values taken off. We can remember those values and then recreate an analog signal once we need it. But this is the resolution of horizontal. How do we define this vertical resolution of the amplitude? Well, let's say that the amplitude has, and in this case, believe me, this is a very bad resolution of sound, but let's say that it has a very bad resolution as such. 3, 4, 5. 5 is enough. Let's say 6. Okay. So if a computer needed to remember this value of this dot in time, so the value of the signal at that precision time moment, he could not remember 1.3. As I told you already, we have either 1, 2, 3, and so on. So he would remember this dot as the closest one. As 1, it would be right there. So at this point in time, it would be 1. At this point in time, it would most probably not be here, it would be 3. It would be right there. So this one can just go away. Yep. Let's go back. So it would remember it right there. This one would be remembered on 3. This one on 4. And actually that one really coincides with where the values are. This one would be 4 point something. Actually, it would remember that as 5. This one would also be 5. This one would also be 5. This one would also be 5, right up there, like straight. This one would be, let's say, 4 down. This one would be 3. So now if we needed to make the signal analog again out of this digital one, see these dots that we have as results, like this one, that one, that one. Now we get a completely different signal because our resolution was bad when we sampled it. It's called sampling. So taking these discrete values in time is called sampling. So once we sampled it, we had a really bad resolution. And now, on account of that, once we recreate that signal so that we could actually play it through our speakers, it's really bad. The reproduction is really bad. Now, let's actually talk about resolution of audio. So, every MP3 you have in your computer most probably has the resolution, time resolution, of 44,100 hertz. That's the most common standard one. Let's say something common as a CD has exactly that time resolution, 44,100 times a second. It will take one of these values. So every 44,100 times every second, so each second 44,100 times, it's going to take one value, and that's really dense. If you think about it, if this was 1 second right there, it would have 44,100 points on this axis right there, just up to that point. So that's really dense. So it would take many more of these, values, and this grid of these dots explaining, representing this analog signal would be so dense, it would be so precise. you might think, and it actually is, because that's your CD resolution, and it is really precise. As you know, by listening to music from CDs, it sounds really clear. Now, why is it 44,100? Well, the scientists found that humans hear frequencies up to 20,000 hertz, and then by testing found out that if we double that frequency in our digitalization of audio, we can fool the ear into hearing an analog signal, so making the digital and analog signal indistinguishable by humans. Any higher resolution than 44,100 will not add any distinguishable improvement, and even though our sound cards and computers might be able to create and record digital audio at higher resolutions, the toll on the processing and memory is probably not worth it, and it will not improve any perceivable quality. If we talk about this amplitude resolution right there, well, on a CD, it's 16-bit. Now, what would that mean? That means 2 to the power of 16. That's how many dots, these dots, I call them dots because that's what I draw, but just to make it clear for you, that's how many values we have from maximum here to minimum right here. So from minimum to maximum, right there, we have 2 to the power of 16. That is 65,536. Yeah, that is how many values we would have right there. So really a lot of these dots. So the problems I talked to you about with having low resolution, that really doesn't transcribe even to the most standard and most common commercially used digital product we have for years already. Just imagine when the CD came out, and that was a long time ago, we already had that resolution. So 16-bit, this is how we call that, 16-bit, 2 to the power of 16 divisions here, and 44,100 divisions each second. That's really a lot. Now imagine how this amplitude resolution could also rise up. So let's say we have double of this precision. So we have 88,200 hertz. That means we had another dot in between each one of these. So add another division. So we take twice as many measurements, and let's say we have 24-bit resolution. 24-bit would be 2 to the power of 24. That's 16 million. 16 million divisions right here from minimum to maximum. That's a lot. And that's not even the highest resolution used in music production today. So we get up to 192,000 hertz. We can say 192 kilohertz. Like that. So we have 192 kilohertz, and we can get this bit depth, as it's called, the resolution of the amplitude, all the way up to 64-bit point float. Yeah, so 64-bit resolution of audio. 64-bit, you can imagine how much bigger that is. If going from 2 to the 16, from 658,000 to 2 to the 24, which is 16 million. Can you imagine how great this resolution is to represent our audio? It's insane. But just for you to grasp it, how really detailed this digital information is. Now, when we get into sound waves, and sound waves is just like this sine wave that I explained to you. Let me delete all of this and draw you another axis system so you can actually get a good representation of this too. So far, what you've seen in my drawings was only a sine wave. That's the most simple electrical signal, which is, as I've told you, also present in your wall outlets. Now, aside of sine waves, we also have other waveforms. If we looked at the most common and most basic sound waves we have, we could see that we have, let's say, a sine wave, and then we could see that we have a square wave, like that. a square wave. Then we would have a triangle wave, and we would have a sawtooth wave that just repeats itself like that. Okay, so let me draw that more dense so that you can actually get what I'm talking about. So a saw wave, that can actually be inverted just like that, go upwards. So ramp up instead of ramp down. So those are the most common and most basic sound waves and sound forms. But why am I showing you this? It's to understand that, many times I'm sure you have already seen some software, and you probably haven't, but even if you haven't, somewhere you've seen a sound wave representation in a movie. Watching those, spy movies, you can see how sound waves are represented many times as squiggly lines, just alike the sine wave that I just showed you. Yes, and those are moving. Why? Because they're representing the sound that is actually being produced at that moment. So they're momentarily following the sound. So to explain this to you, we're going to talk about how speakers produce sound. I'm going to need this picture of a speaker membrane from a profile and cut out like this. So what this is depicting is a speaker membrane, and the cone it has on its back end connected to it with a coil running around it, and of course a magnet running around all of that. So once we run electricity through this coil, the electricity goes in through this wire, goes around the coil, and gets out through the other end of the wire. It produces a magnetic field that reacts with the magnet, pushing the membrane outwards. And then when the electricity goes the other way around, through the wire and through the coil, it pulls the membrane inwards. You can see that on the graph right next to it, that when it's in its positive phase, this is when we have our membrane being pushed out. And when it's in its negative phase, the membrane is being pulled in. Now, this pulling and pushing of the membrane actually creates air pressure. It moves the air vibrates, and then we hear that vibration of air as sound with our ears. So it's as simple as that. The electricity goes one way, pushes the membrane, goes the other way, pulls the membrane, and this alternating quickly back and forth makes vibrations in the air, and we hear that air vibration as sound. Now, if we were to check how the membrane moves when a signal, just like this one, a sine wave signal, goes in, the membrane would actually create the same waveform. So the membrane would move the same way that we see this sine wave. It would slowly go forward, and then it would slowly go backwards, following this wave shape of a sine wave to the letter, to say. Now, if we had a square waveform to move the membrane, it would still follow this square to the letter. So it would not gradually go out and go in as, push outwards and inwards as for the sine wave. But for the square, we just jump out in the positive phase, like right here, and then it would just quickly move inwards and hold that inwards position when it is in its negative phase, and so forth. So it will follow the waveform that we provide with the electricity to the letter. So what this speaker is actually, this combination of this membrane, the coil, and the magnet, is actually an energy converter. So it converts electric energy into acoustic energy, into sound pressure. Now, we could use this the other way around. In the example I just showed you, we are providing electricity, which in turn, using the coil, produces a magnetic field, and that magnetic field reacts with the magnet, pushing the membrane in and out, producing sound pressure. Now, if we produced sound pressure and applied that sound pressure to the membrane, we would have electricity produced in the coil. Why? Because when you move a coil in a magnetic field, the electricity is generated inside the coil. So we would get electricity generated inside the wire. So if we moved the membrane inwards using sound pressure, we would get the electricity generated in one direction. And if it was pulled outwards, it would generate the electricity in the other direction. So the same thing, just the opposite way around. We are providing sound, and in turn that sound moves the membrane, and membrane, having the coil attached to it that's surrounded with the magnet, produces electricity that we use to actually
have sound recorded as electricity. So a microphone is nothing else but the same version of a speaker, at least dynamic microphones, the same version of a speaker, but the membrane is just much smaller so that the air pressure we provide with our voices could be enough to move it sufficiently to produce enough electric energy so that we can record that as sound. So that energy converter that we know as a speaker can be used in two ways. It's either converting electrical signals into sound or converting sound into electrical signals.